Okay, yeah. So thanks everyone for coming. It's my great pleasure today to introduce our speaker, Yanan Ye from Beijing University, who will speak to us about pluriclosed flow and Hermitian symplectic structures. So thanks.
Thanks for Professor Street's invitation. And today I'd like to talk about my recent preprint about the pluriclosed flow and the Hermitian symplectic structure. Firstly, let's review some basic notations and facts about pluriclosed flow and the Hermitian symplectic structures. A metric is pluriclosed if it satisfies dt bar equals 0, and the pluriclosed flow we can write it using the bismuth connection. As omega values. Here, rho 11 is the 11 part of bismuth rich form. The bismuth rich form is rich form with respect to the bismuth connection. Bismuth connection is unique. Is a unique connection satisfying the three conditions. That is, it is the Hermitian connection, and the tensor induced by torsion is a 4, is a 3-4. And meanwhile, we can use another form of pluriclosed flow today. Use the Hodge operator. It is star omega and its contribution. And the first chain class. Okay, this is about pluriclosed flow, and I'd like to talk something about the Hermitian symplectic structure. Very shortened as HS structure. We see manifold admit a Hermitian symplectic structure if there exists a Hermitian symplectic form. The Hermitian symplectic form is firstly introduced by Professor Streets and Professor Tian. It is omega is a Hermitian symplectic form. If it is a real and closed to form, such that its one part is positive. If we rewrite it as here phi is 2 0 form, it's a 2 0 parts and omega, sorry, small omega. And omega is the 1 part. Then it is closed, is equivalent to this equation. And we notice that this the 1 part, this metric is Flory closed. By this equation. So for convenience, we can say a Flory closed metric is Hermitian symplectic if it is the 1 part of some Hermitian symplectic form. This means if this means a Flory closed metric is Hermitian symplectic if and only if there exists a 2 0 form satisfying this equation. And I'd like to talk about some history about the Hermitian symplectic form. One of the motivation is if we consider the Flory closed flow, just like the Ricci flow or Taylor-Ricci flow, we consider the possible simplest solution is like if we have a Einstein type metric for some constant. N is a solution. So we'd like to find the metric satisfying this condition, and Street and Tian call this metric is static. If when the coefficients is not 0, then is a Hermitian symplectic form. So we can find a natural Hermitian symplectic form induced by a static metric with lambda not equals 0. This is because rho is Ricci form. So it is real and closed. And this condition, omega 0 is a static metric, so its one part is positive. But unfortunately, we have proved that there are, we state that non-Kähler surface on Kähler manifold admit this structure, but it is not clear. It is not clear. It is not clear. This problem is not clear for the high dimensional case, and they ask a question. There exists and this is the motivation of this is the motivation of my paper. I'd like to find a flow that preserve and I hope the Hermitian symplectic form deform along this flow may deform to a Kähler form. So this may be a way to answer the question asked by Spritz and Tian. Very fortunately, we observe that Rory closed flow preserves Hermitian symplectic structures. We do some explanation for maybe we write it as a theorem. Recall that we have say a pluriclose metric is a Hermitian symplectic if it is one part of some Hermitian symplectic form. That means it can be extended to a Hermitian symplectic form. And then if the initial condition is address, we need to prove that the solution is address or equivalently find two zero form satisfying and the proof is simple. We apply D to the Florey-Close flow, and the right hand side is d bar star omega, then omega t is here the Hodge operator is with respect to omega s. Recall the initial condition is Hermitian symplectic, so we can find a 2-1 form satisfying the equation and break exchange dd bar operator. Sorry. So we can define phi t as phi 0 like this, and it satisfies this equation, the second equation. The only thing is to check that phi t satisfies the first equation. And this equation gives us motivation to consider the evolution equation of phi. That is, and if phi t is the solution it satisfies this equation, then we can rewrite it as like this. We want to rewrite it as a evolution equation of phi. It will be 1 minus 2 factorial star and use the relationship between d omega and d bar phi. Make it this is here is outjoint operator of Lefschetz operator, and we add a coefficient. And this equal is because we use a lemma for 2-1 form. Sorry, wait. This lemma can be proved by directly computation. And then now we have the evolution equation of two zero parts, and we can put them together. This is a special case of the Flory closed flow discussed in their book. They consider the Flory closed flow coupled with the evolution equation of two zero form. And this is just a special case. And here we have a more relationship between the 1,1 part and the 2,0 part. Now we can define a law about permission symplectic form. Where the initial condition phi is a Hermitian symplectic form. That means
so the first equation in your flow, it should be with the one part of the Bismuth-Ricci form, right? Rather than the two zero.
Yeah, sorry. Yeah. 1,1 part. Sorry. Thank you. Yeah, we have shown that this equation have a solution in short time because the phi can be defined like this, and the first equation is just a Flory closed flow, so it has the short time existence. And we need to prove the uniqueness of the solution. The only thing we need to check is that the uniqueness of the second equation. Actually, we have the next lemma. And this type of equation is a parabolic equation. Or it's a smooth family of metrics. And phi zero is declosed. And then we can prove about it. Firstly, we observe that if phi t is a solution with initial condition is D closed, then the solution phi t is declosed at any time. And we also in local coordinates phi x phi ij, which T is which GZG. Here the coefficients is skew symmetric. Then we compute the right hand side. And take trace with and D to plus which G because there is a minus. And we need to only need to check to clear the second order term. We check if it is the elliptic operator. It can be rewrite as PIQ. So the coefficients is skew symmetric, and note that the solution phi is D exact. So represent what is phi is D exact equals phi ij k plus phi j k I plus phi j. So this is IPJ plus phi ji. Here IPJ PGI, so it is minus JIP, that is IGP. And so we complete our proof. It is a parabolic. It is a parabolic flow. So we have the uniqueness of the solution. That is,
Sorry, Yanan.
Yeah.
So it's also right, I guess, that in this setting, this operator is the 2-0 part of Bismuth-Ricci, is it right?
yeah. This is just the 2-0 part of Ricci, and I would say we can rewrite it as this. If we put them together. This flow can be rewrite as this part is actually the two zero part of the Ricci. And if we use this form, it is easy to see that it preserves the closed condition. But at first, I didn't know. At first, firstly I get this equation, and at that time I didn't know it is just the two zero part of the Ricci.
I guess, yeah, I mean, it is a different way to think about that. I mean,
Yeah.
it's a very different expression, I guess, for this 2-0 part in this special case, I guess.
Yeah, and I'd like to take a little time to give another viewpoint of the proof to prove that this equation can preserve this condition, although we have proved it. Now I give another viewpoint. That is, firstly, I state a lemma that it is like above. It is a smooth family of metric, and beta 0 is I'd like to see beta is 214, and the initial condition is D and D bar exact. Sorry, closed. D and D bar closed. Then the solution, if the solution exists, it is D and D bar closed. Or it satisfies this equation. And the lemma says this equation is also parabolic. And I'd like to skip the proof. If we have this lemma, then we can see that the evolution of the 1-1 part is very close flow, and its torsion or its d omega, it satisfies d bar star omega, and we rewrite it as minus 2 star, and use the lemma again that is just d plus first log, and the evolution equation of the 2-0 part. It also satisfies, recall that it satisfies this equation, and apply the bar operator. We have minus or is it R A trace R Y maybe R trace. Now, if the initial condition is satisfied this equation, then we can say that the omega t is a solution to this equation, and minus d bar phi is also a solution. With the same initial condition. So if we have this lemma, it is harmonic, so by the uniqueness of solution, we prove again that it preserves the Florey-Close condition, the second equation of that condition. See the second. HS condition. That is, we just give another proof, and this is the first proof I find, and fortunately, and later I find a simple proof. That is, we state here. Yeah, this is the simplest proof I find later. And now we have and now we have and now we have the evolution equation of Hermitian symplectic form. And we prove it is harmonic. It has a short-time existence and the uniqueness. The next question I'd like to ask is how long it can exist, and will I find a topological obstruction out this flow? Firstly, I will define a functional. We denote the sets all Hermitian symplectic points on manifold M, and define a function A, positive functional by here we write it by parts. phi k is 5 wedge itself k times, and this is the inner product induced by the metric. Here, for the reason of a degree, actually it is a finite sum. And the first term is the volume. So this functional is strictly positive. And we can consider the function dividing along the solution to the flow if omega t is a solution to this flow. And we prove that we stated omega t is a solution to then Vt is actually a polynomial. With respect to time of degree at most. Here n is a dimension of the manifold. And the coefficient can be written as we take the sum from 0 to the key such that 2k plus I equal or less than a dimension, and there are some coefficients. Minus 2k minus I. One and integral only depend on the initial condition and the first chain class of the manifold. And minus 2k minus I is 51 0 as 4. And AI is only depend on the initial condition and the manifold, the first chain class, especially En is factor of 1, and here only have one term that is k equals 0 minus 1. So if 0, all these are coefficients are just 1. Here is 0, 0, and k 0 I equals n. So there are only first chain class of n. it is a topological quantity, and so by definition, we can see that Vt is always positive. So if the solution exists then Vt can be defined on this interval, but because it is always positive, so it has no root. And especially if we care the global solution of omega t, that means a global solution, or a global solution means that this solution exists on half 0 to infinite. If omega t is a global solution, that means to infinite on the manifold. And this quantity must be non-negative, because it is the coefficient of the top term, and Vt has no roots. So AI must be non-negative. If the coefficient of the top term is negative, it must have a root on this interval, because Vt will be negative as t approaches to infinity. Thus, we find a topological obstruction to the global solution. It is only determined by the first chain class of the manifold. It is independent of the initial condition which you choose. And I'd like to skip the complete of the complete proof because the computation is boring, and we consider the simple case to find how to prove this theorem. The dimension is 2, then Vt can be written as I. This is, and this, and notice that when dimension is 2, this quantity or the norm of phi is independent of the choice of a metric, because it's the middle form, and we compute its derivative. and the abbreviation. This is data star plus its conjugation and the structure comes. Consider we can do this term. Integral by parts and note. This is one form, so there is positive. And we can return this term. Integral by parts. And using the fact that if omega plus y equals 0. So take multiplication by y. So these two terms plus these two terms equals 0 and their configuration is 7. The remainder is we have and here note that this is not well defined. This function is not well defined. But if we fix a background metric, then the difference is well defined. So we rewrite it as determinant plus and using integral by parts twice and note that omega is very close. Then the first term is 0. This is the derivative of V and we compute second derivative. It is just omega dot, which this term. And because this is a closed form, a real closed form, so the first and the second term is 0 just by the integral by parts. So the only thing is and this is a constant. So it shows that Bt is a polynomial of degree at most 2. And the general case, the proof of the general case is similar, but the computation is more complicated. And if our time is enough, then I will give the sketch of the proof and the last. And now I'd like to talk something about the surface case, because they are more interesting thing in this situation. Firstly, I introduce a function. Actually, it is monotonic. Firstly, we define the function. Ft is the norm of phi around the flow. Actually, the norm is independent of the metric features, and we have the proposition that Ft is here phi is a solution. Moreover, if the initial condition, the omega 1, omega 0 is not, non-chiral, then Ft is strictly decreasing. This observation is simple to prove. We compute its derivative. And its combination. And this term is within integral by parts. And the fact that the phi bar is the bound. And this is where exchange the two form and rewrite the bar star. D star omega. Note that now we are in the surface case. Is 2. So star omega is just omega. So it is the norm of that is the derivative is just and if the initial condition omega 0 is non-chiral, then the solution is always non-chiral, because if the initial condition is chiral, the Flory closed flow is just a chiral-rich flow at So using this position, we can consider the limitation of the Fourier closed flow with Hermitian symplectic initial condition. This state as so. Omega t is a solution. So that the initial condition is Hermitian symplectic. Sorry, it's a global solution. And if it converges at infinite time, then the limitation must be tighter. This is because we can consider the norm of phi. Recall that omega is a Hermitian symplectic, then it satisfies this equation. The first equation is always satisfies because phi is a two zero form, and if phi equals 0 or phi is closed, then omega is chiral. Actually, we can show that the limitation, the phi with respect to the limitation is 0, because we have ft as this. This is just one bonding bound. This is F2 omega s. So and there's ft less than f0, because ft is always positive. By definition, it is a norm. It is a norm of phi. And this is true for auto. Because we assume the limitation is exists, so must be 0. That is, it is chiral. Actually, although I didn't find a monotonic function in high dimensional case, but this result is still true. And now I will give a proof of those Professor Spritz's method. She told me another proof to show this in any dimension. If omega t converges to omega infinite, then actually is state solid of generalized Ricci flow. That means there exists a simplest function such that G star H here. So three form is just the torsion form in our solution case, in the very close flow case. And we consider this. This is D star, and this is G star and G bar. And here is a 2-1 form plus 1-2 form. And there are 4 parts. The first we do the D star return into this 1 form and 1-2 form. And sorry, D bar star operator and at 1-1. So we check the degree, then we find that, which is a by degree, then we find that the omega is 0. It means this one. And then we consider the norm. The weighted norm. Because the initial condition is Hermitian symplectic. We assume it is Hermitian symplectic. So the limitation is also Hermitian symplectic. This is just there exists on 2-0 and this is and this is the weighted norm on torsion. The limitation is Keller. And I'd like to talk about another application of the decreasing of F. Recall that if lambda not equals 0, then lambda 0 omega is H Hermitian symplectic if omega is static metric. That means and for static metric, for example, then the solution to the very closed flow is 1 minus lambda t. Similarly, the solution to the O2 to the 2 form is also like that. And especially the 2 zeros. So we compute again the t in this situation. And just because ft is decreasing, so we must have lambda. Lambda is not equal to 0, so we must have lambda positive. So actually, there are no static metric like this. And in dimension 2. Because if lambda is a negative constant, then ft is increasing. It is a contradiction. And I'd like to give another viewpoint of the evolution equation of 2 zero form in dimension 2. Or is d star omega. D star in dimension 2. Star omega is just omega, and use the relationship that this is d bar phi. And because phi is 2 zero form, and in dimension 2, we have and this is just phi. This is d star phi. And because the phi is exact, so no. So this is minus. That is the half-life version because to phi. And then notice that this is elliptic. And we can, and if we use this form, if we consider the evolution equation by this viewpoint, then we can give another proof of the decreasing of f. That is because phi omega t, but it is independent of the metric. So it is just a function. And d star one. Because here it is only have the part d star one. In general case or in general dimension, actually, we also can rewrite it as I, but there are another term in the right hand side. So maybe it have a monotonicity of some function, but I haven't prove it because I didn't know whether the extra term is positive or negative. But in the surface case, they are just zero. And we still have time, and now I'd like to give the proof, give a sketch of the proof to the obstruction theorem. That means we compute the coefficient of Ricci. We just need to derive it and derivative it again.
Sorry, Yana.
Uh,
You're saying this form, you say you can think of the evolution of phi in dimension 2 as the Chern Laplacian,
yeah.
but not in higher dimensions?
In the high dimension case, there are another term. So it may not be a hit equation, but there is something, maybe some term or order less than 1. Maybe we can compute it now, and I think it's a little interesting in the surface case. And we compute this. That's the evolution equation is so fine. And so star, or there is embossed. And this is just one. D star, and this is and let me see. I wanted to computer. Sorry, I see. Start by and we compare this on that. This is and plus 1 down 2.5. So it's can be like this. Minus and the first term is this is just and this is just be we need a minus because phi is prime, so by the Lifshitz theory we can this will be this there may be some coefficients and this is just this dot phi, and because we have divided is 0, so this is the Laplacian, and we have the second term in high dimension. The second term is just this dot and which and if we regard this equation as the equation of phi, so they're just order less than 1 because we just take the operator once is the order less than 1. And in the case n equals 2, this term is second term is 0. So in high dimensional case, it may not be a hard kernel, but add something. And I don't know. This term is it? This term is definite. I'm not sure. Yeah, and then I'd like to give the speech for the obstruction theory. Here we state two. No, we computer is first. In this case, and 5k. Here, because phi is 2-0 form, it is prime. So this can be right as is a confidence and point which phi which and we computer its derivative. Sorry, yeah. Sorry, maybe I lost the coefficients. Yeah, sorry. Here has a coefficients like this. And formally, it's just like if we define the exponential function to a true form, formally it will just like it's just to be like maybe the exponential by smaller. Sorry, here I forgot the coefficients. It's just factorials n minus and y derived this and its computation and we will derive omega. We derive here using the evolution equation and integral by parts. The first term will be K and this actually y star is d star omega and integral by parts. This is d exact, so we just have two terms. That is d star omega h y minus 1's power and d y which y bar h. And here has another key. Because here it's n minus 2k. N minus 2 and the second term can be like this. That means here recall that omega is d star omega and d star omega and plus the first term is, and we represent these two. And the integral by parts we also have two terms. The first is this is phi. Is d bar. Is phi. D bar phi. And small page. And its configuration. Sorry. And n minus 2p minus 1. Install page 1 omega page 2. Okay. And this is the configuration, just like this configuration of this one. So we just have these 4 terms and their configuration, and this one, the Chen class. Yes. Then using the fact that those the coefficients that this term, the coefficient is k times n minus 2k, and this term is also k times n minus 2k. And using the fact this is d omega and this is d bar phi. So there are zeros. And note this term we can rewrite it as, if we denote 8, we denote alpha t of omega is 5, h omega minus 2. And there's this alpha k is. Then this term is a squared Victoria squared minus 2. Alpha minus 1 and 2. And this is just to represent it. This is k minus 1 factorial squared. And this coefficient is factorial n minus 2 k minus 2. This is k into 2, and using the fact it is big pi1. It's just like that. This is there are for the fifth term, and we have a sum. This is a derivative of the case term, and we have a sum. We claim that Okay. We claim that the sum is 0, and just to check it, because this is k minus 1, and for the k plus 1, the k plus 1 term, this is k squared minus k plus 2, and 1 k 3 h to the point, and this term is minus k plus 1. So the only thing to check is that the first term and the last term is 0. And we skip it. So if we derive the function bt, we only, this is a reminder. There are some coefficients, and this form omega, the power of omega minus 1, and we add a chain class. And similar to the case of surface, we need to check, we need a lemma, because here this term is dependent about to time 2. We need to change it to a fixed background metric, and to do that, we need it wedge or very close metric. We need to check it to, just as the case of surface, we need to, there is a very close metric, and we have the lemma that this one, maybe we write it as S, this one, here, some coefficients. It is floricals. So applying this lemma, then we can, this is just the sum of this term, because this is just the sum of this term, because we have a sum. This is just the derivative of this term, and we have a sum. So applying this lemma, we have that. Just change this term to the power of omega minus 1, and add a chain class. Sorry, something wrong. Sorry, there is something wrong with it. Oh, okay. It's just, that is here. The power of the omega minus 1, and there is a chain class with respect to our background metric, and we can derive it again. Here we need another lemma that is which is just or y is d and d bar closed real form. It is 2R form, 2S form. Then we can complete the proof by induction. That's all I want to say today. Thank you. Any questions?
Yeah, great. Thanks. Yeah, thanks. Are there any more questions?
Yeah, I just have a comment about your result, your argument about long-term existence of pretty-close flow plus Hermitian symplectic, sorry, implying Keller. Yes, if the flow converges to a metric which has vanishing Bismuth-Ricci form, then there is another argument of the Keller condition which comes from my paper with Jeff and Josh, which is that so the metric will be Hermitian in a holomorphic Courant algebroid, but the fact that it is Hermitian symplectic implies the holomorphic Courant algebroid is holomorphically trivial, but it has a subbundle which is the holomorphic cotangent. So it is a split, but it needs to be a split in the frame given by the own metric, and the second fundamental form is essentially the L of omega. So you get vanishing of the torsion. So this is another way of.
Actually, I don't know if split.
Oh yeah, it means that it's holomorphically split. It means that in principle the holomorphic vector bundle that you construct out of a pretty close metric is an extension of the tangent of the holomorphic tangent by the holomorphic cotangent. But if the metric is Hermitian symplectic, this means precisely that the bundle is holomorphically isomorphic to the tangent plus the cotangent. And this condition plus the fact that you have a Bismuth Hermitian metric gives you that the metric is scalar. It's just another argument for the same thing.
I haven't considered this question, and I don't know how to answer it. Maybe a tangent vector bundle, and a cotangent vector bundle.
Yeah, I mean, this is it's not a question, it's just a comment that there is a third argument, if you wish, of how to prove this scalarness when the full Bismuth-Ricci form vanishes in the limit.
Yeah, he just has an extra argument for this coming from a generalized geometry point of view.
Generalized
for the Kähler rigidity.
Sorry, I don't just a little about the generalized geometry, and
maybe I just make one more comment. I think this fact that that the Bismuth 2.0 is the Chern Laplacian of beta, this should be true in every dimension. This is essentially computed in my papers, my paper with Josh, where we prove this Calabi style estimate, this estimate for the churn connection of the generalized metric. Sort of implicit in those computations at the beginning of the paper is a proof that if you have this Hermitian symplectic condition, or like if del omega is del bar beta, then the 2-0 part of the Bismuth-Ricci is exactly the churn Laplacian of beta. That's true in every dimension. I can send you afterwards. I can send you proof of that.
Oh, thank
Yeah. But yeah, all right. Is there anything else? Okay. Well, yeah. Thanks, Yana. That was very interesting.
you.
Thank you.